Okay, so I guess we can probably get started. Well, I'm probably just going to introduce our speaker, then we can wait for people to join. So I think we are really honored to have Dr. Wei Han from Manchester join us, give a talk today about machine learning-based intelligent control drones. So I know Wei, so we are kind of colleagues back in Delft when I was a postdoc, and Wei at that time was assistant professor at TU Delft. Wei had a really amazing career, so he has been actually in both industry and also into academia. So after graduating from Imperial College London, he went down to do actually I think it's kind of a research manager or managing position at DJI, which is one of the most famous company in the world which manufactures drones. So after that, after DJI, he went back actually to academia to join TU Delft as an assistant professor. And then where he is now actually, and I think he actually leads a Delft neuromorphic AI lab. So he's the co-director of Delft neuromorphic AI lab. So then he moved to Manchester. So he moved from Netherlands to the UK as associate professor, so senior lecturer in Department of Computer Science. He's a member of Center for AI Fundamentals and the Center for Robotics and AI at Manchester. He's also the director of teaching at the new CDT, which is Manchester on AI, which is probably a sibling kind of CDT with our Safe AI CDT, which is hosted here at ISA. So I believe that Wei will give us a very nice talk. He promised that he has a lot of videos of drone flying. So I hope that it will be really interesting for everybody. So take it away.
Thank you very much. Thanks, Jihong, for the invitation. It's very nice to come to York to give this talk. And today I'm going to talk about machine learning-based intelligent control of drones. So basically, a brief introduction of myself, my background, although kind of in addition to the nice introduction from Jihong. Originally, I was trained as a control engineer. Okay. Then at Imperial, I began my journey on machine learning. Okay. Then I went back to DJI, work on the combination of control and machine learning for drones. Then we met some problem. So basically, we're trying to use reinforcement learning to control drone back in 2017. So it doesn't work in the real world. I mean, like 7 years ago. So that's why motivates me to come back to academia to pursue kind of more fundamental research on learning for robotics. Then I met Jens Kober. And Jens is the supervisor of Jihong. So you see, this is basically history. Then in 2022, I found that maybe there's some emerging technology over there, so which is the foundation model and so on. So that's why unfortunately say goodbye to Delft and to be a senior lecturer in machine learning, actually. So that's why I'm in the Center for AI Fundamentals. So that's kind of the route. Okay, so today I'll tell you a little bit more about how we use learning for drones. Okay, so this is the contents of my talk. First of all, I'm gonna give some background of drones and machine learnings. Then I'm gonna introduce reinforcement learning for drone control. Then after that, okay, it's gonna be the system identification and model learning for drones. Then after that, I'm gonna move from single drone to multiple drones, talking about a drone swarm and the coordination control. And the last, I will give the conclusion and outlook. So drone technology is demonstrating its enormous potential across various fields, from aerial photography to light shows, from logistics delivery to aerial taxis, and from agriculture irrigation to wind turbine blade cleaning, to applications of drones continue to expand. However, the current limitation on large-scale drone applications are insufficient because insufficient intelligence, inadequate decision-making capabilities, and the lack of real-time autonomous decision-making ability, especially in complex environments with communication interference and disconnection. The research on intelligent drones continues to innovate and develop. To summarize, intelligent drone systems are composed of three key elements: intelligent agents, interaction modes, and behavior rules. By mapping the characteristics of flying organisms and the biological swarm systems to drones and the drone swarm systems, we can identify four key characteristics: self-organization, self-adaptation, self-learning, and self-emergence. These characteristics enable drones to interact with their environment in real time, make autonomous decisions, cooperate independently, adapt to changes, learn from feedback, and develop emergent behaviors and capabilities that exceed the simple sum of individual contributions. So next, I'm going to talk about the reinforcement learning-based drone control. Okay, this is a single drone. We're going to talk about two topics. One is the robust and safe policy learning based on Lyapunov stability theory. And the second will be Bayesian reinforcement learning for safe policy optimization in uncertain environments. In drone technology, reinforcement learning helps achieve autonomous decision-making through intelligent control. The method works by letting agent learn through trial and error, interacting with the environment to maximize the long-term rewards. It focuses on two aspects: modeling state action spaces and training through repeated decision-making sequences. Reinforcement learning is used in drone control because, first of all, it handles large state action spaces with real-time needs. And second, reinforcement learning autonomously explores decision strategies through interactions with the environment. And moreover, reinforcement learning continuously learns and adapts to environmental changes online. And lastly, but not least, reinforcement learning explores and obtains optimal strategies in unknown or dynamic environment. From DeepMind surpassing human players' scores in video games in 2013, to AlphaGo defeating professional players in Go matches, to AlphaStar beating the World Championship runner-up in StarCraft, and Alpha Dogfight winning over human flight pilots in close-range aerial combat. Reinforcement learning applications have made tremendous progress. The state and action spaces of the problems being solved have become increasingly high-dimensional and closer to the real world, with technology advancing at an accelerating pace. Reinforcement learning has begun practical applications in robotics. The University of Zurich used the reinforcement learning to achieve autonomous high-speed flight for racing drones through tracks, mainly employing model-based reinforcement learning methods. And OpenAI used the reinforcement learning to enable a robotic hand to solve Rubik's cubes by itself. Boston Dynamics robots learns to open doors using reinforcement learning and imitation learning. Currently, industry has begun to applying reinforcement learning to real-world scenarios. With its powerful autonomous decision-making capabilities and exploration, trial and error capabilities, reinforcement learning shows broad application aspects. However, in practical applications, robot system design and operation must consider issues of stability and safety. So, what is stability and what is safety? Stability typically refers to a system's ability to return to its equilibrium state or maintain expected behavior after external disturbances. Safety refers to ensuring the system doesn't pose risks of harm to equipment or the environment during operation. These two aspects are crucial for ensuring normal and reliable operation of a robotic system. In control theory, system stability is usually determined by using Lyapunov functions, while safety is often evaluated through control barrier functions. These methods provide theoretical guarantees for system stability and safety. However, in traditional control system, deviations may occur due to coordination issues between different modules, of course, because the system is so complex. Could we design an end-to-end control policy where control policy outputs directly and act on the actuators to avoid inner module deviations? This is one of the research goals of reinforcement learning algorithms in recent years. Additionally, reinforcement learning algorithms face the same two real challenges in real robot applications. The difficulty of transferring from simulation to the real-world environment. Therefore, in complex safe control tasks, we are currently exploring whether we can ensure system stability and safety by building a performance evaluation function that combines learning-based method with rule-based knowledge. To describe both safety and stability, we introduced the control Lyapunov barrier function, defined as follows. When the system state is at the desired position or equilibrium point, control Lyapunov barrier function, or CLBF, the value is 0. One is not. CLBF value is positive. CLBF can also distinguish between the safe and unsafe states. When the system state is in the safe state set, CLBF value is less than a constant C, right here. Okay, right here. So when it enters to the unsafe set, CLBF value is greater than C. If we can design a controller meeting these constraints, okay, we can guarantee system safety and stability. However, constructing the CLBF control Lyapunov barrier function and finding controllers that satisfy these constraints is highly challenging. So essentially, if you can't find a Lyapunov function or control Lyapunov barrier function, it's kind of like an energy function for the system. So if the derivative of this energy function over time, in continuous time, or the difference between the next value function or energy function of the next state minus the current one, so is negative, okay, basically saying that it's kind of the energy is decreasing over time, we can use this inequality to verify the stability and the safety. So this is kind of the informal understanding of Lyapunov function or the conditions. So in our case, to deal with such a complex system and the robotic system, we propose a neural network-based construction method within the reinforcement learning framework. Within the reinforcement learning framework, we design a cost function or reward function if you want, because typically in control, we are using cost function. We try to minimize something, but instead of maximize the reward. So this is kind of the difference in terms of the terminology, okay? So we design a cost function to construct a state value function as the desired CLBF function. So that's the key. So the state action value function gonna be the Lyapunov function candidate or the control Lyapunov function candidate. So that's the key. Yeah. So meanwhile, we optimize the control policy using the constraint optimization framework. So essentially, okay, you want to minimize or maximize the value function, and if we search this value function, okay, under this constraint, then we can solve the problem. So you can use any method, for example, like Lagrange multiplier or other constraint optimization framework. So in this way, if we can solve this optimization problem, so we can find the safe and stable policy that can be applied to the robotic system. So as you see here, okay, on the upper right corner, so we demonstrate the test result after 1,000, 1,500, and 2,000 training episode. So if you see the dark blue right here, this represent the unsafe regions, and the light areas, okay, represent the safe regions. So the darker, the unsafer. So the lighter and more safer. Okay, that's the explanation. So if you can see as the training episode increases, the white color, the safety bounds, okay, that's the safety bounds, gradually approaches to the obstacle area. So this is the obstacle. So it's like kind of projection of the 2D environment. Think about it, okay. So think about it, there's a drone gonna fly over here and get past the avoid these obstacles and get to the target point. So of course, the target point is the safest part, right? So essentially, if this region or the value function or the energy bound is kind of larger, so meaning that, okay, we are starting from the safe region. And interestingly, if you look at here, this figure, so this is after training for 2,000 episodes, that if you see here, this region is very dark, right? Meaning that during exploration, the drone never go to this region. Why? Because typically drone is flying like this, right? They'll never fly with a large curvature. So it's like this. So this is kind of a more physically making more sense. Yeah. And additionally, if you look at the in the bottom figures, we conduct a test from different initial conditions because you're going to try from different initial conditions and see if it can converge to the final point. If from the lower figure, we can see states starting in the safe region can safely reach desired position, and state starting in the unsafe region cannot complete the task. This is known as the region of attraction in control theory, saying that if you can determine the safe initial state, well, these states will be the safe starting point, and which is called the region of attraction. So we hope that the robot can start from the region of attraction, and eventually it's gonna be guaranteed to converge to the final safe goal. Okay. So these simulation experiments verify the feasibility of the control policy, and meanwhile, the control layout and barrier function can serve as an effective means to evaluate controller performance. And we test our approach in both unmanned vehicle trajectory control and drone navigation tasks, directly transferring the control policy, which is modeled as a neural network, trained in simulation environment to the real-world robotic platform for validation. So in the unmanned vehicle tracking control tasks, if you see the upper right, okay. By the way, this is done in Delft, so I think Jihong is very familiar with this room. So the proposed control policy achieved the process trajectory tracking within the specific aero range, ensuring vehicle stability and safety in complex environment. And if you look at the lower figure, so in the drone navigation task, as you can see here in the previous slide, okay, from the safe region, avoid these obstacles and get to the target point. Okay, this is like a more 3D real world visualization. So the proposed control policy successfully avoided obstacles and accurately reached the predetermined position from various starting points. However, other safe reinforcement learning algorithms encountered collisions with the obstacles in this task. Through testing in these two tasks, we verified the effectiveness of our proposed method in real-world robotic platform applications. Next, I'm going to introduce a very special type of drone, spacecraft or satellite. So rendezvous and docking technology. So this is kind of in the aerospace term. Basically, it's like a goal reaching with collision avoidance. So that's the rendezvous and the docking. Okay, but it's a bit complicated. But I will skip that due to a time limitation. As a key technology in the space mission, so plays a very important role, especially in space station construction and the satellite maintenance tasks. The technology not only directly affects the mission success, but also determines the safety and efficiency of the space missions. Okay, that's important because goal reaching and collision avoidance is so important, of course, also in space. So the difference between the space and the ground environment is what? No gravity or very low gravity. Okay. So that's the key. So spacecraft must operate in a special macro low gravity dynamic environment where even small thrust changes can significantly affect their orbital trajectory. And additionally, the varying lighting conditions in space are complex and changeable, greatly affecting spacecraft visual sensor perception capabilities. To overcome these challenges, spacecraft typically employ a multi-sensor fusion perception, and it is necessary to perform uncertainty quantification, okay, precising on the multi-source input data. If we are using reinforcement learning, we need to construct a state value function that considers these uncertainties. So by combining Bayesian policy optimization method. I'll introduce shortly in the next slide. Okay, explicitly, estimation of the control policy and its gradient can be achieved, enabling stable online optimization of spacecraft control strategies to adapt to different task requirements and complex environmental changes. This Bayesian approach not only enhances spacecraft intelligent perception capabilities, but also effectively improve the stability and safety of the rendezvous and the docking process, providing technical assurance for successful space mission implementation. Okay, a little bit technical. In reinforcement learning, we know that we want to maximize the reward and long-term and value function. You want to minimize or maximize the value function and so on and so forth. And our goal is to find the optimal control policy that minimizes the value function, basically. Okay, and define the control sequence. Okay, so how can we achieve that? So basically, we're using Monte Carlo. We collect a lot of data and take the average. So that's the classic way. Now we do that. And it is notorious to know that we need a lot of data, for sure, right? And also, importantly, the estimation is rubbish, basically, because the variance is so high, yeah? However, in the Bayesian integration method, okay, which is known as the quadrotor. So this is like a kind of a Bayesian way for the integration of functions, okay? Since the state action value function going to be described by something, we're going to use Gaussian process instead of a deep neural network to approximate the policy and the state value function. If it can be described by Gaussian process, we know there are a lot of nice properties regarding Gaussian process. The integral, derivative, everything are still Gaussian process. So in that sense, we somehow can get an explicit representation of the policy gradient. Here we go. We know Gaussian process can quantify uncertainty, right? But somehow it's kind of a closed loop. We sort of have a way to incorporate the uncertainties I mentioned previously in the perception and the intermodule coupling and so on, so forth, right? So if you can see on the left figure, so the right figure, the policy gradient direction in the Bayesian integration method shows significant uncertainty difference across different parameter directions. So these differences might be caused by varying sample data distributions, and optimizing policies along these high uncertainty directions might lead to unstable control effect. And to address these challenges, we propose a more stable, uncertainty-aware policy optimization method that ensures uniform uncertainty across different policy parameter directions. Okay, and this will help improve the stability and the reliability of the control policy. Okay, so to simulate the space rendezvous and docking scenarios on the ground, we built a ground-based microgravity hardware-in-the-loop simulation platform. So it's kind of like a skating ground. So, and everything is floating. It's kind of pump the air to lift the simulator. And this simulator is not like a kind of, because I'm saying this kind of special drone, but it uses ducted fans, you know, to push the air to change direction and motion of this satellite. Yeah. So we again, as previously introduced, we directly transferred the control policy to the spacecraft simulator for testing, and the results show that the spacecraft simulator successfully completed rendezvous and docking tasks with the target spacecraft without entering no-fly zones. Okay, and however, other reinforcement learning algorithm and MPC exhibited some strange behavior during testing, specifically by moving away from the spacecraft waiting to be docked. So that's the video. Actually, we also try to combine deep neural networks with Gaussian process. So essentially, in the feature extraction, we're using a deep neural networks because to deal with high dimensional sensor data. But in the last layer, we are using the Gaussian process. So essentially, the Gaussian process is kind of an online tuning based on the data you observe, right? So this gave a very nice property for the spacecraft or satellite or kind of customize the robots to adapt to the changing environment and by using the uncertainty quantification. So that's the take-home message for this part of the work. So Bayesian policy optimization method considers the data information uncertainty, solving model inaccuracy and data noise issues in complex robotic control problems, thereby improving policy generalization and robustness. So the above was our work on autonomous decision-making and control. Now, I'd like to share a crucial topic in the drone field, system identification and the model learning. And I'll introduce three aspects: online modular adaptive control of area manipulators, drone dynamics identification based on diffusion models, and edge competition-aware online drone dynamic system identification. So please look at the images on the screen. At a first glance, these drones seem to be performing various tasks. However, these seemingly ordinary scenes actually had many challenges. The drone over farmland experienced continuous mass changes as it sprays pesticides, and the drone flying near the ground or buildings may face complex air disturbances or malfunctions. And the drones flying over water must deal with unstable airflow caused by surface reflections. These are all disturbances from external environment on the drones. There are also some less obvious factors. For instance, drone battery gradually deplete over time, affecting power output. Rotors may experience minor wear from prolonged use, just broken, right? Impacting their performance. Even changes in air humidity and temperature can affect the drone flight's characteristics. It is these factors that make the actual dynamics model of the drones extremely complex and uncertain because of these environmental factors. We can't simply rely on the preset fixed models to accurately predict and control drone behaviors. This is why we need system identification and model learning to learn the dynamics from the observations. The first work I'd like to introduce is the online modular adaptive control of area manipulators. Okay, an area manipulator, as the name shows, consists of two parts, drone and robot arm, okay? So this enables the manipulation kind of movable in 3D space. So to make the motion more easy or kind of extend the range for area manipulation. And it can be basically for the desktop tasks like moving object, grasping, picking into place, and drilling and assembly. So it's like kind of a flying robot arm. And however, if you know that, so the drone dynamics per se is very complex. And the manipulator per se is also very complex. And the combination will become complex and complex. That's why, because the reason of the coupling between the two robots is the key reason to make the dynamics so complex. Yeah. So as introduced in the previous slide, uncertain environmental conditions add another layer of complexity to these dynamics. So consequently, area manipulators are expected to have the ability to learn or identify their model in an online fashion, so during flight. In the control community, this is a well-established research area known as adaptive control. Firstly, okay, a little bit of mess, but it's okay. It's nothing but middle school physics. No worries. Okay, Newton law. Okay. So first of all, we're going to use the classic physics-based Euler-Lagrange method to derive the drone dynamics equations. So this method gave us standard dynamics formulas, including, yeah, I can use this, mass matrix, Coriolis matrix, gravity vectors, disturbances, and input, and so on. Okay. If look at here, okay, these three equations, okay, we can divide the area manipulator dynamics into 3 subsystems, okay? Position, attitude, and the manipulator. So for drawing is nothing but a position and attitude, right? And the other dynamics will be the manipulator. So what is the advantage of this division? It allows us to design controls independently for each subsystem without interference. So this is one of the innovations in our method. However, there's a challenge here. If you look at the mass matrix, okay, so this is the mass for the position attitude arm, is for sure, right? But if you look at this coupling term, okay, although it's kind of parameterized, but if you really want to figure out what is the exact value of these coupling factors, almost impossible because of the coupling dynamics is so complex. We don't know how they come. Yeah, they interact with each other in the off-diagonal elements. Similarly, the correlate matrix, gravity vector and disturbance vector face the same issue because of the coupling issues. Although we have the parametric form of dynamics, the specific values are basically remain unknown. So how do we deal with these uncertainties if we don't know these parameters? Our solution is to combine all these unknowns into a unified uncertainty term right here. It is important to know that we introduce a new concept, M bar, okay? If you look at that, M bar, MPP bar, P dot dot, okay? So this M bar is different from the original mass matrix. Here, M bar, okay? This is the M, okay? So this M bar, P double dot, is considered as a nominal system. So what is a nominal system? It refers to an idealized mathematical model representing the system's expected or typical behavior and the normal operating conditions. So this model serves as a benchmark for designing control systems and analyzing system performance. So essentially, we roughly have an idea what is the model about by using kind of the diagonal elements, and all the rest are uncertain. These are model uncertainty. So everything else, we don't know, we don't care. We just care about the linear part, all the nonlinear, whatever, uncertainty. Yeah. So by introducing this nominal system, we can better handle the differences between the actual system and the ideal model, providing an important foundation for our adaptive control strategy. Now you must have a guess. Okay, you have a linear model, you have more uncertainties. You must have a way to deal with these uncertainties. Yes. Now let me explain how exactly we design an adaptive controller to deal with those varying, changing over time uncertainties. Okay. So in the control flow diagram, okay, we can see 3 blue subsystems, submodules, as I mentioned before, okay, position, attitude, arm, okay. A modular online adaptive control module right here, okay, calculate the adaptive gains because we know control, we're going to use PID, right? So PID, the number is like called gains in control theory, okay? So basically, this module, okay, we're going to explain later, going to calculate these gains that can be used for drones, like a PD or something if you want. So position and attitude control are arranged in a cascade sequence, yeah, which is the typical outer loop and inner loop control strategy or structure for quadrotor control. It's very typical, yeah. The control allocation matrix is used to calculate each rotor speed using thrust control input, tau P, and a torque control input, tau Q, from the outer and inner loops. This modular approach allows us to control complex aerial operation systems more flexibly and robustly. On the right-hand side, let's use the position dynamics as an example. So it also applies to attitude and arm. So that's why you see P, epsilon P right here. So in this subsystem, all uncertainty terms are contained in the epsilon P, okay? We take a conservative approach by first deriving the upper bound
of this uncertainty epsilon p. And this upper bound can be parameterized as a linear combination of some parameters, well, like feedback and constant, the feedback arrows, and the square, and the second order information. But this is nothing but a linear combination of some observations. Well, all these parameters k, p1, p2, p3 are unknown parameters. Okay, this is kind of nothing but a linear combination. Okay, we assume, okay, this is like this, but don't ask me why. But there are a lot of kind of a theoretical work and books to explain why it works. Yeah, okay, yeah. So if we have this upper bound, then we can use these combinations to give a rough description or linear description of what is the uncertainty going to look like. Okay, if you look down, moving to the adaptive parameter learning. So based on the online data, including the feedback arrow, control input, and the normal model, so we can fit this epsilon p, this model uncertainty, because we have the data, we can calculate. We have the measure of this, then we know this, right? Basically, we can calculate this, right? So we just use least square, to fit these parameters, the k hat, to be the kind of the model or description to fit or learn the model uncertainties. Now, if some perturbations occurs in the model uncertainty term due to uncertain dynamics or external disturbances, so the k value will change, and this in turn will update the k hat term. Okay. If you look at the control rule design, the final control law consists of the three parts: a feed-forward term for the dynamic compensation, and the linear feedback arrow term for tracking desired trajectory, and adaptive gain term for handling uncertainty. Yeah. So the advantage of this design is its ability to adapt to system changes in real time. When the system encounters unknown disturbances or dynamic changes, the controller can quickly adjust to maintain stability and performance. And again, we use Lyapunov stability theory to provide a stability guarantee. So that's why I'm asking, don't tell me why, because we have to make assumptions and mathematically, therefore we can prove. So you can use whatever you want, but if you can't prove the closed loop stability, give the assurance and guarantee, we will not use that, unfortunately. Yeah. So you can't use reinforcement learning, per se to do that because it's so unsafe and no guarantee for that. So this adaptive mechanism applies not only to position control, but also to attitude and arm. So through this modular design, we can handle uncertainties in each subsystems independently while maintaining overall system coordination. Okay, now let's look at the specific pick and place task. First, the drone takes off and begins to moving towards the payload position. When it reaches to the target position, the robot arm extends and uses the magnetic gripper mounted on the end effector to grab the object. After grabbing the object, the drone begins to moving to the payload's placement position. And during this process, I want to draw your attention to a particular detail. As the drone moves, the robot arm simultaneously adjusts its angle, moving in the opposite direction. So why this task is particularly challenging? Because there are inherent coupling effects between the drone and the robot arm. A disturbance is one system directly affects the other. For example, the movement of the robot arm changes the center of the gravity of the entire system, and conversely, the drone's motion also interferes with the process position of the robot arm. And finally, the area manipulator system reached the target position and successfully placed down the payload. Next, let's look at the perching function. So inspired by the perching behavior of eagles, we use an intelligent gripper as the end effector in our system. The key feature of this gripper is that it immediately grabs once it makes the contact with the targeted object. This design mimics the rapid and precise movement of eagles when catching prey, allowing our drone system to achieve quick and reliable grasping while approaching target at high speeds. Next, let's discuss impedance control. Unlike instantaneous grasping task with loads, right? Hybrid force and the motion control involves two simultaneous tasks. First is maintaining a predefined trajectory, and second is maintaining constant contact force with the wall. So this scenario is applicable to tasks like high-rise building cleaning, and a power plant or inspection. Yeah. So our adaptive control treat the wall's reaction force on the robot arm as an external disturbance and update its gain accordingly. Yeah, you can imagine, right? So it's like, then you have to feel it and you have to learn the parameter, basically. That's the key. So in the area manipulator control example, there's an assumption that the upper bound of the model uncertainty epsilon can be parameterized by a linear combination of the observations. Okay, linear combination. Well, if you can approximate that using a linear combination, why don't you try neural networks? Yeah, if you can use the neural networks, so basically the learning capability, the approximation is gonna be better, right? Yeah, let's do that. Yeah. However, okay, a big however. So in the real world, these model uncertainties can be very stochastic and non-parametric. Can neural network work? Yeah, let's have a try. So for example, factors such as downwash, humidity, and wind gust can be very difficult to measure. So the model uncertainty is strongly dependent on these factors, resulting in multimodal nature. Okay, this multimodal is not a multimodal perception or the foundation model. It's like a multimodal distributions, like Gaussian distribution, but there are a lot of hills and values, and so on and so forth. That's the multi-modal distribution regarding the model uncertainty. Okay, so in this figure, we confirm the multimodal nature of the model uncertainty during real-world flight. So even under ideal environmental conditions in the lab, okay, we implement a standard PID or PD controller that allows the quadrotor to track a flower shape trajectory. Okay, then since the experiment was conducted under ideal lab conditions, the model uncertainty epsilon can be calculated. However, we observe different magnitude of the uncertainty. If you look at the colored, the right part in the figure, even in the same segment of the flight path, when the state and the control input are the same, so you see the difference. Essentially, in simulation, they should be exactly the same, right? But in the real world, it's different. So that's why it shows the phenomenon of the multi-modal distributions. If you look on the right, in this figure, we use different machine learning models, such as Gaussian process, deep neural networks, GPT-2, along with the diffusion model to estimate the model uncertainty epsilon for the flight path in the red box. Since epsilon is high dimensional, we project it in 2 dimensions using TSNE, a well-known dimensional reduction technique. And we observe that the diffusion models, the last one, the right one, can most accurately capture the true distributions. Why does diffusion model work? Have you heard of how diffusion model? Diffusion model essentially, OpenAI Sora is like from text to images. So this is kind of the model we're gonna use. Well, it somehow makes sense, right? So, but in here, we're not generating images or videos. We're generating the dynamics or the model uncertainties. So why does diffusion model work so well? Diffusion models are typically used for generating images from noise. So here is how they work. Small amount of Gaussian noise are iteratively added to an image until it becomes pure noise. Okay, this process can be described as OU process or any variance preserving stochastic differential equation. A neural network, for example, UNet, which was initially used in medical segmentation. Yeah, so is then used to reverse the above process. That is from pure noise to images. Instead of generating images, okay, we want to use the diffusion models to generate the model uncertainty from sensor data and control input. Okay, if you look at the right, this can be achieved as follows. So during training, we collect the data, including sensor feedback, okay, and a control input, and a calculated model uncertainty, because we know the torque, we know the nominal model part, right? So we just calculate. It's nothing but a supervised learning to fit that, right? So we then add noise to epsilon during forward process. So the neural network will predict UNet, by the way, to predict the amount of noise added to epsilon. This is the optimization process. And during inference, we sample noise and iteratively denoise it to estimate epsilon from sensor feedback and control input. So we're not using the data to build a neural network to predict the model uncertainty, but rather use a neural network to predict the noise. Then you can denoise from the data and to reconstruct the model uncertainty. So that's the kind of the way I want to explain, instead of using the vanilla neural network to do that. Yeah. So now we have a machine learning model to accurately estimate the model uncertainty. So now that we have a trained model, how do we use it in control the quadrotor in real time? Okay, the quadrotor will track the desired trajectory using a feedback controller. While the quadrotor is flying, feedback data are collected and fed into the diffusion model. The diffusion model iteratively denoise a sample of the Gaussian noise epsilon capital T. Yeah, right here. Capital T is just nothing Gaussian noise in T time steps to generate the model uncertainty epsilon hat. So the model uncertainty epsilon hat can now be used as a feed-forward dynamics composition in the adaptive controller. So remember the previous adaptive controller? So now we are using this diffusion model as the feed-forward composition. Yeah. Again, this framework allows us to guarantee closed-loop stability based on Lyapunov theory. And also, we have to use some assumptions regarding diffusion model in the machine learning theory community to give an upper bound for this diffusion model. So with this upper bound, we can use Lyapunov theory again to prove the stability. Yeah. So the diffusion model based adaptive controller can achieve rapid tracking of system states and has better robustness in disturbances, rejections, and the payload changes. So let's see what happens. To verify the effectiveness of the method, so we conduct a challenging task with external wind. We place the two fans to generate the wind gust. This scenario is very common in real-world scenario. Well, the drone has never seen that in the training process. So everything has happened just to kind of, I know, to make sure the generalization is good. So as we can see, the drone is stabilizing itself to its desired set point against the wind to hover. Here, we only consider X, Y, we don't consider Z. So let's just look at the X, Y rather than the Z axis. So because our approach enables effective short-term adjustments, as well as low compensation for dynamic variations, ensuring both robustness and accuracy. Thus, it outperforms other controllers. For example, L1 adaptive control using Gaussian process as a model, deep neural networks, GPT-2, and this is the diffusion model. Yeah. Oh, by the way, this rope has nothing to do with the control. It's just to ensure safety, in case the drone crashes somewhere. But anyway. So one of the other evaluation criteria is to test the framework on the ANSI training data, of course. So in this case, so the quadrotor is tasked with carrying a payload of 0.4 kilograms with an average velocity of 0.5 meters per second on a complex flower-shaped trajectory, okay, which involves sharp turns and curvatures. And the quadrotor is not specifically trained with this payload and velocity. However, as we can see in the performance chart, our framework outperforms all other controllers. And furthermore, we trained the payload to 0.8 kilograms, a more challenging scenarios where the quadrotor is not trained. And again, we can see that the framework outperformed the other method. So the reason behind such outstanding performance is the diffusion models really, really good at generalizations and learn the multimodal distributions. So we have seen good results from machine learning in drone dynamic system identification. However, for drone to adapt to complex and changing external environment, machine learning models often need the real-time online training on the drone side or on the edge side. Before working on the large models, let's take a classic Gaussian process for the online dynamics model learning as an example. How can we deploy it on drone edge computing platforms and ensure control real-time performance and stability under resource-constrained conditions? We described the previously mentioned Euler Lagrange dynamics equation through a Gaussian process. Specifically, the system dynamics can be represented using a state space equation in classical control affine form. The Gaussian process is characterized by the mean and the variance. The mean represents the expected or average behavior of the system dynamics. The variance represents the uncertainty in the dynamics predictions. Through the observation data, we can estimate the posterior mean and the posterior variance through the Gaussian process regression. So the key to solving the posterior is calculating the inverse of the Graham kernel matrix. The Graham kernel matrix describes the correlation between the data points. However, the computational complexity of the matrix inversion is cubic in terms of the data size, which poses a significant challenge to the drone's onboard computational performance. So how do we address the computational challenge posed by the inverting the Graham kernel matrix? So that's the key for the online system identification of the drone dynamics on edge devices, on drones. So computing the inverse of a Graham kernel matrix is equivalent to solving the linear system. We know that linear system can be solved through iterative optimization algorithm, if you see on the right-hand side. So we know that, for example, like a contributed gradient method or Newton method. So as you can see on the right figure, we first discovered that the matrix inversion and the Gaussian inference in Bayesian learning have a dual relationship. The mean of the Gaussian distribution in the inference process is equivalent to the result of each iteration calculations. And meanwhile, the variance of the Gaussian distribution can characterize the error in iterative calculations. So using the perspective, okay, right here, we derive the expectation and the variance of the Gaussian process solutions at the S iteration. Here, uncertainty can be decomposed into data uncertainty due to finite data and the computational uncertainty due to finite computation. So the figure in the lower right shows that for a given batch of data, as computational power decreases, if you see the blue variance, okay, in the bottom line, the data uncertainty represented by the blue remained unchanged, okay, while the computational uncertainty represented by the green gradually increased from 0. At the same time, we find that the region of attraction, okay, which is the safe region where the system initial conditions lie, become more conservative as computational power decreases, which align with our expectations. So we applied the proposed online system identification method to drone trajectory tracking control tasks. So we have the drone carrying half a bottle of water where the fluid sloshing dynamics would cause disturbances and the center of gravity changes. Using Lyapunov theory, okay, we construct system stability conditions represented by this inequality. You see the right here. Yeah. That we introduced earlier. It's very similar to the reinforcement learning part. Okay. So in this inequality, to ensure tracking control stability under finite computational resources, we consider the effect of both computational uncertainty and the data uncertainty. Then we can use the second order cone programming optimization to solve the controller optimization problem with stability guarantees. So all the competitions are using an edge GPU, for example, NVIDIA Jensen Orin, or maybe something lighter. Yeah. So next, I was showing the tracking errors with and without considering computational uncertainty and the different computational power levels. So the control task is to track a figure 8 pattern. So when using the full computational power, the tracking errors are very similar. So of course, you use all the computer resource, right? So this certainly matches our intuition. However, if we use 50% of the computational resource, the average tracking errors, computation agnostic controller becomes worse, while computation aware controller can still maintain the tracking performance. If we reduce to 20%, so the average tracking error for computation agnostic controller become even worse, while computation aware controller can still maintain the tracking performance. So next, I'm gonna move to the multiple drones, which are drone swarms and coordination control. I'm gonna introduce multi-drone cooperative pursuit based on cooperative theory and the large-scale drone formation based on learning predictive control. So swarms distributed control originated from the field, such as biology and ecology. So this is a lot of explanations of phenomena in the real world or in the nature world. And we're mapping these phenomena in the natural world to the drones. So which can be for example, fixed formation flight drone swarms, temporary formation, and cooperative hunting by drone swarms. And distributed swarm collaborative control strategy can be divided in several parts like consensus, formation, pursuit, and collision avoidance, and connectivity, maintenance control, and so on. So let me first introduce our work on the multi-drone cooperative pursuit based on cooperative theory. So the question is how to solve the problem of collaboration breakdown when encountering unknown teammates, improve multi-agent systems adaptability to unseen co-players. From multi-agent cooperation perspective, they essentially belongs to a pre-coordinated teamwork. So pre-coordinated teamwork is achieved either through coordination mechanisms provided by an oracle, okay, predict, yeah, or through cooperation patterns gradually established during the long-term interaction and the learning process between agents. However, the pre-coordinated teamwork method faces cooperation failures when unknown teamworks or unknown teammates join. Therefore, how to improve multi-agent system adaptability to unknown teammates and ensure sustainable cooperation is of great significance for real-world applications of multi-drone systems. So zero-shot coordination is an effective approach and the research direction for solving the unknown teammate adaptation problem. Different from the pre-coordinated teamwork, zero-shot coordination emphasized the ability of agent to effectively collaborate with unknown teammates without prior training or communication. Existing zero-shot coordination research mainly defines the problem as a two-player Markov decision process, aiming to solve the zero-shot coordination challenges in two-player video games like Overcooked and Hanabi. So how do we solve the zero-shot coordination problem in the real-world multi-drone cooperation tasks? Specifically, the goal of zero-shot multi-drone cooperative pursuit is to train a single drone agent learner to collaborate with N-1 unknown pursuer teammates to capture invaders within a fixed time without collisions. So current research mainly focuses on the pre-coordinated teamwork, such as multi-agent reinforcement learning, which cannot address how to cooperate with unknown teammates. So we designed a physical experiment environment, so measuring 3.6 meters by 5 meters. So with a corresponding simulation scenario on the right, we use 5 crazy fly macro drones with 3 as pursuers and 2 as invaders, along with 5 obstacles. And each drone has a limited perception range. The pursuers and invaders are randomly generated in designated area, which increase the variability of the experiment. So to address the zero-shot multi-drone pursuit problem, so we are using graph theory and game theory. So we first review the cooperation incompatibility problem in zero-shot collaboration. Although the overall reward increases, the ability to collaborate with some teammates doesn't improve synchronously. So to evaluate and solve the cooperation capability problem, we propose the previous graphic form game. Okay, so due to time limitation, I will skip this technical part. And the model basically contains overly complex information, making it difficult to for the analysis. So we are using the preference graphic form game as shown in the middle figure. Yeah. So to address the cooperation capability problem, we propose a cooperative open learning framework. So the core of our method is maintaining and updating a set of policy models called population. It can adaptively adjust the learning objectives to achieve dynamical learning. And we also theoretically prove that the framework can converge to the local optimal preference agents. So as you can see here, so this is like in the video game, and the AI and also an unknown teammate will join, and they will finish the hook job. Yeah. So based on the early theoretical research, we extend it to multi-teammates. So I think we'll skip that. Let's see what happens. So basically, we introduced two sets of experiment. The first one is called a homogeneous pool. So basically, the drone with the same kind of algorithms trained. And the other experiment is called the heterogeneous pool. So the drones with different kinds of algorithms. So in the homogeneous partners, so we can see 3 pursuers and 2 invaders. So let's start. So if you see this one, this is quite smart because it's kind of like a surrounding. So just in the middle path. Yeah. So let's see the heterogeneous one. So basically, they are trained with different algorithms. Okay. So there are 3 pursuers and there are 2 invaders and some 5 obstacles colored in blue. Let's see what happens. Okay, capture. No. So from the videos, we can see that our approach can somehow generate kind of a strategy, like in the military books. So kind of to capture the invaders. And the last, okay, I will introduce our work on the multi-drone formation control. So basically, we have discussed a lot on the reinforcement learning advantages. However, reinforcement learning has the limitations in scalability. For example, think about deal with 10,000 drones. Can they do that? Probably not. And the real-time online learning capabilities, very difficult. Yeah. However, we found that a classic method called model predictive control, control theory can do that. Can we somehow combine reinforcement learning and the model predictive control? So the idea is that we are using the actor critic to learn, the cost of function or the value function, and also we're using neural network to represent the policy explicitly. Then if we can learn the value function and the policy under the model predictive control framework, okay, seems we are using reinforcement learning to solve the MPC problem. But the difficulty is on the theory part. So you have to prove they are equivalent. Then you have to show the convergence. You have to show the optimality, and also you have to show the stability. So, but anyway, if you are interested in that, read the paper, and then there are like the 10 pages of proof for that. But basically, it works. So let me show you how it works. Yeah. So basically, in this case, let me demonstrate the effectiveness of the policy learning. And due to limited space and budget, we don't have 10,000 drones, so we can only do in simulation. So let's show the simulation result. So you see the leader and you see the followers. So they're gonna do the formation. So this is not only happened for the direct deployment, but also you can learn online, because essentially in model predictive control, you do the online optimization, right? So in this sense, we are trying to learn these policies online in real time on drones. Yeah. So next, kind of a more real in Gazebo is like, if you can realize in Gazebo, it can work in practice more or less. Yeah, because it was hardware, PX4, and low-level control and so on. Okay. So in this case, we visualize the 40 drones in different formation configurations. You may wonder why 40? Because the GPU rendering for the Gazebo is only support 40, but essentially you can do more. Yeah. So this is like a 40 drones large curvature path following, and this is continually for the 40 drones formation keeping. So think about what's the application. It's like in the light show. So think about it, if you have an idea, you want to show some graph or formation, just to send the signal to the drones, then it just show the name or something for advertisement or for entertainment. Yeah, just for fun. Yeah. And the last is strict line tracking. Yeah, because this is kind of intermediate, input of the tracking trajectory. Okay, just to send a signal to them then. And also, the most importantly, is like a distributed manner, because the drone only connect or communicates with its neighbors. So it's not like a centralized. So that's why that's the beauty of distributed nonlinear MPC. That's why you see the reason. That's motivation. Yeah. Okay, and the last, okay, I'm not a guy who like simulations a lot. I like the real world deployment, but due to budget limitation, we test on 3 vehicle unmanned vehicle formation. So if you see if there's an obstacle, so the leader try to avoid this obstacle, then maintain a triangular formation. So you see the car just wiggle around, go back a little bit, and they perceive like a narrow corridor in front of them. So they'll change the formation to a line to go past or bypass the narrow corridor. And after passing, they will, okay, resume the triangle formation. Yeah. Okay. So conclusion. So I introduced the 2 things: single agent or single drone and multiple drones. And on single drone, I introduced reinforcement learning for control and decision making, and system magnification and model learning. And regarding the multi drones, I introduced the cooperative theory for pursuit problem, and also the combination of reinforcement learning and MPC for very large or ultra scale drone formations. Yep. I think I keep that, and thanks to all my students who did excellent work on this. And any questions? Yeah. Thanks.
I think due to time, we probably will get 1 or 2 questions if you have any. Anybody, yes, please.
Thanks, that was a really interesting talk. I had a question was about the system identification. I don't think we know about to decide where you.
Yeah, let me do this. So which part? The online thing, right? Yeah. Yes.
So my question was really how much of one of the dynamics when my computer is how much of it you're computing versus approximating. So for example, are you computing mask matrix or are you taking these so the terms like the set of position of those games you take that. My second part to this question is always like if you are computing those things, what does the internal representation of that look like? So are you computing them in terms of system level?
Yeah, so this is a very good question. So basically, we're kind of like a little bit, simplify the problem. So we only consider the navigation, like a 2D navigation thing. So it's you can confidently use Gaussian process to model the kinematics basically in 2D dimensions. So if you can do that, then it's fine. But the problem is that if this dimension is very high, for example, you consider orientation, you consider z-axis, it's a bit challenging. So we are working towards that. So so this is I think this is the first part question. So basically, in this case, we're just starting working on this direction, and we want to just show that this phenomenon exists. But you can extend, for example, using deep neural networks compared with like a fixed informed neural network, as the feature extraction part, then you can add a Gaussian process afterwards. So essentially, you try to tune the last layer. It's very much like the Bayesian reinforcement learning part I introduced for the satellite. So this is a kind of there's a trade-off between that. But essentially, the key ideas are still there to quantify the computational uncertainty for that. Yeah.
So you've done it.
Yes. Yeah. So what's the second part? Question?
Oh, it's really it's related to this.
Yes.
What's the kinematics again? For the internal representation.
Yes.
Like how you, for example, use 6.
No. So in this case, it's like a very simple case, like planar, planar drawing, like 2D thing.
Any other questions that you would like? Yeah, please.
So if I understand it correctly, maybe I'm wrong. So based on this presentation, it seems like the decision-making model of this system actually takes account of most of the internal uncertainty of dynamics and the coding stuff. Have you considered the external uncertainty of like environmental uncertainty, how you can incorporate those into the decision making?
So basically for us, it's like we think about the problem. Yeah, this is a very good question. I think this is more related to perception. Okay, I'll ask this. So basically from this perspective, we see everything external as uncertainty. So we really don't care about the source or the reason that caused this uncertainty. But if you consider more complex environment, I agree with you. So I think you should consider more on the perception side. For example, you can use a say the fancy foundation model to understand everything and do the representation, do the feature extraction and so on and so forth, and as a part of the word model. Yeah, but so far, as I show here, just because that's the title, right? I want to focus on control, so kind of a more control theoretical perspective. But if you consider the word model, it's going to be challenging. So, but I think we are working towards that, and also the community is working towards that, because this is so important regarding the perception part. Yeah.
If there's no further questions, let's thank the speaker again. Thank you very much for coming.